Hey everyone, welcome to another episode of Robo Papers. Super glad today to have Xinhang, one of the co-authors of this paper called Trace Anything, representing any video in 4D via trajectory fields. Thank you so much for making the time, Xinhang. Perhaps you can share a little bit about yourself.
Yeah, sure. So thanks, Chris and Michael, for having me. My name is Xinhang, and I'm currently a PhD student at HKUST. And my research interest is in 3D reconstruction with application in AR, VR, robotics, and also spatial intelligence.
Mm.
Yeah. So
Awesome.
maybe I can get started. Yeah. So I'd like to first talk about, start with the problem of 3D reconstruction, which is a very classical problem in computer vision for decades. So the target is to recover 3D reconstruction, a 3D structure from of an object or the environment from a collection of 2D images. And the traditional computer vision way of doing this is structure from motion, which has also been developed for decades. And but if you think about the problem of 3D reconstruction or to reconstruct a world, you need to see that the world is actually dynamic. And sometimes when you input such a video is also capturing a scene, environment and objects. But if you feed such input into SFM pipelines, they can fail estimating camera poses and this 3D coordinates. And also another point is that a single point cloud, it is not enough to describe the thing because you have motion here, you have dynamics. So a single point cloud cannot describe it. So that's why there's currently no consensus on first what representation to use to describe this kind of dynamic things, and second, how can you acquire such a representation? And of course, you can run SFM. Sometimes it can fail, and if it succeeds, it only give you a static point cloud. Basically, it frees every time step into a same time step. So that's not ideal. Yeah.
Sorry, Xinhang, for those who are new to this, could you explain a little bit what's SFM?
SFM. So SFM is the traditional way of doing 3D reconstruction, and its pipeline runs through several stages, and basically it is it uses a sequential way to do this task. It first get 2D matchings from pair of images, and then after you get all those correspondence, they run optimization based boundary adjustment to estimate to find the camera pose of each of the camera, and also find the 3D coordinates of these key points in the 3D world. And it is kind of similar to the SLAM problem in robotics, which you also have, let's see, on a vision SLAM. You have visual input, which can be video or collection of photos, and you want to localize each photo. Also, you get the structure of the whole environment. So this is a problem. And I was just describing the high level idea of SFM, and there are very mature software protocol to do this task and implementing this SFM. Okay, so talking about 4D and dynamic things, I'm saying SFM may not work. And personally, I do a lot of research on this 4D representations. So back in 2021, we did this freeview point video. So freeview point video means a video that can be viewed at any viewpoint, which means you can put it in your VR headset so the user can view it from different angle. And this project will give it editability. So this giant is actually me, and I'm putting my first author surrounding me. This is based on Nerf. Later I can talk a bit about Nerf. And this, so for this work, this later work, we improve the training and inference efficiency of all such nerve or Gaussian splatting based representations for dynamic things to achieve better, because you may want real-time inference if you consider applications on VR and AR. And later I did a project that gives you free viewpoint video with object level tracking, like this. So user can give some interaction, and then we can do no view rendering as well as tracking. And another aspect is if you consider the microscopic work, the basic element of our life is biomolecules. They are also dynamic structures, but you are not recovered from photos. You need to recover these structures from cryo-EM images, but they are also dynamic, so you need a dynamic representation, not a static one. Yeah, so that's my exploration around 4D representation. But largely, if you consider all these 4D representations that are derived from nerve or 3D Gaussian splatting, they can give you very good quality, rendering quality for all your immersive experience, which means they give you very good appearance. But they have a lot of shortcomings. First, they need to be captured. Most of the case, if you want very good dynamic nerve or 3D Gaussian splatting, you need this complicated capture like this. And also, it takes a lot of time to train such a representation, and it can give you very incorrect modeling of geometry and motion. If you look at the dynamic 3D Gaussian splatting, you can have a motion that move leftwards, but if you look at you visualize all the trajectories of your splats, it can even move rightwards. So this is nothing true, and not physically grounded. And also another thing is it is hard to align with other modalities. So this can restrict a lot of downstream applications. Yeah. So that's why we consider doing something new, and we did this project. So in this project, basically what we achieve is something like this. So we give a representation of this input video, and the user can actually exploit in a visualizer. So you can see the background, which is fixed, which is static, and the foreground, we reconstruct this motion in 3D. And we also extract the trajectory, we call trajectory field here, this is a visualization to really describe how is everything moved here. So yeah, so we propose trajectory field as a novel dynamic scene representation. Trace anything is a neural network to estimate trajectory fields from your input video or image collections. So this is what we did.
So is trajectory fields basically the points in 3D space that is inferred to be moving, and then but across frame, across time. So you're tracing.
Yeah, I think you can see that, and later I will break down how we define trajectory fields. Yeah, basically you can view it as 3D point, but we keep track of its movement across different time steps. Yeah, so over last several years, people did some work following Duster. So Duster is basically it can be seen as a 3D foundation model now, I think. So basically did the traditional 3D reconstruction task, but in a deep learning manner. They train a network to map images to 3D structure. But before that, people mostly think this is not possible, but they did a very good job, and they achieved that. And doing this in a end-to-end manner, the strength of this manner is that if you do traditional SFM, because you have a sequential pipeline, the errors can accumulate. But when you do it end to end, somehow this is more more ideal, and different part of the pipeline can help each other. And I think what Duster tell us is that I think the most correct thing they did was to do this mapping. They map image from 3D point map, which means H by W by 3 to H by W by 3. And actually 3D point map is a bit different from point cloud, I think, because for point map, you have alignment with image on the level of pixels. And then with this alignment, you can imagine a lot of downstream tasks to do because image, so now I think we can say image can be well aligned with language. And maybe if you can do this well, although it is not a cheat, if you can really align the 3D point map or its feature encoding the inherent 3D structure with image, then you can also align it with text, and you can do a lot of interesting things. And also do this in an end-to-end manner. You have a network to reconstruct it and encode it. This can serve as that's why this can serve as a foundation model, which is 3D aware. So it has a lot of good point. But basically, it map image to 3D point map and map one pixel to one 3D point.
May I ask a clarifying question there on
sure.
3D point map versus point cloud? So you're saying, so the difference there just is that the point map is basically just an XYZ image. It's like each point, each pixel in the image is instead. Is that what you mean when you say that there's a one-to-one correspondence, or is it something different?
So point cloud. So for point cloud, so point cloud doesn't. Let's say if you get a point cloud from SFM, it doesn't give you the point the coordinate for each pixel, right? It give you some coordinate of your key point, and then you can run MVS to make this denser, but it still not give you very strict one-to-one mapping from a pixel to 3D point. So I'm trying to say they somehow align them in Duster somehow align them in shape. So you use VIT like neural network to do this mapping.
How do you get the data to train this mapping? Like, do you need like really rich supervision?
Oh yeah. Quite a lot of data. So
I guess you get to that soon on your method. So.
Yeah, I believe Duster, at least Duster and also later VGT, faster. They use whole lot of data to train this. So they are using 3D data, static scenes data. Compared to 3D data, 4D data is more scarce. And so we also did some work on data. Yeah, but to train such model, you need to scale up. You need a lot of data. Okay. Yeah, but so for static scenes, you can map pixel to 3D point and image to a point map. But for dynamic scenes, this is still a question. We don't know which mapping to find to really do this modeling. And then if you consider such a toy case where you capture a sequence with this lion cub walking around the tree, you can see you have pixels, and each pixel can trace out a 3D trajectory. Let's say this ear of the lion. It actually traces out a 3D trajectory in the 3D space. And I think this is so pixel is the atomic element of your image or your video, and then maybe we can view the trajectory it traces out as the atomic element of the dynamics of the motion it represents. So this is my gut feeling. And how can we represent a 3D trajectory? It can be a continuous function from a time step normalized between 0 to 1 to a 3D coordinate. So it is a function. And this is also applicable to static objects. So if you consider this, say a leaf on a tree, and let's suppose it is static, we can also say it traces out a 3D trajectory, but it is a degenerate one. So the trajectory so the location should always stay where it is. It is not actually traced out, but it is degenerate. So it degenerate to a single 3D point. So this also applies to static things. Then we somehow try to do this unified mapping from pixel to 3D trajectory. So as I said, a trajectory can be a continuous function from time to a 3D point. So this somehow answer your previous question on how we understand the 3D trajectory. And we do this mapping from each pixel of each frame to a trajectory, to a continuous function. So on the left of this mapping, it is frame ID and pixel ID. And on the right side, it is a continuous function. We map each pixel to a function of time or to a trajectory. And since we do this for we do this for each pixel and each frame, this is very dense. This can be very dense. So we call this a field. So that's why we call this trajectory field. As you can see, we map this ear to a trajectory in 3D, and also this tree pixel also to a 3D trajectory or degenerate 3D point. But it falls within this formulation. Basically, trajectory field is per pixel 3D trajectories. And here I say parametric. This is because the next thing is you need to find a way to describe a trajectory. We haven't talked about that. So basically, this is around this. How can we find a function to really describe a trajectory or a curve in 3D? So this goes to our parametric curves from maybe computer graphics textbooks. So parametric curves, like classical one like Bezier curve and B-spline curve, they represent a smooth curve. It can be 2D dimension, 2-dimension or 3-dimension. They represent a smooth curve using a set of control points. Basically, the parameter of these parametric curves are a set of control points, and you can move your control point to control how this curve is traced out. And of course, if you have more control points, you have more fine-grained control over these curves. And of course, these curves they are smooth inherently. And I think this is part of reason we adopt parametric curve. And later I will, but you still have other way to describe a curve. But later I will describe. I will explain why we choose this as our description of a curve. But this the point here is that we use parametric curve like Bezier and B-spline. Okay, so this is about the representation. So first we answer the question how we are going to represent dynamic things. And if you compare with trajectory field, to other previous solution. So let's say other 4D representation. First, I'm gonna talk about NeRF and 3D-GS based representation because basically they are giving you only appearance. But there are other ways to do 4D modeling. For example, previous people they give you a sequence of point cloud, which means they reconstruct also a point cloud or a point map for each of the frame. But what they lack is they don't got correspondence among frames. So you can have very good point map for each of the frame, but you don't have 2D or 3D 3D correspondence. You cannot know. So let's say the first frame, you have this ear. You can only know its 3D coordinate in this frame's own capture time. You cannot know where it would be in the other frame's timestamp. You cannot know that. But trajectory field is different. It gives you a whole trajectory along this whole time span. It is not a single time instant, but the whole capture time span. This is the major difference. And another way to model for this thing, some people use can say 3D tracking. Basically, you track your first frame, and this can give you correspondence. So you know how these pixels would go across this time span, and also in 2D and also in 3D. But the problem is they only track the first frame. They don't give you the trajectory for other frames. Say, let's say even second frame. If one pixel is not that doesn't show up in the first frame, then we don't know where it goes. Yeah, so that's several difference from other representation, and maybe some merits of our 4D representation. Okay, this is about representation.
So sorry. So each frame, each pixel is predicting both which plate where it is along each one of these parametric Bezier curve, as well as like which other points it's corresponding to, or is it separate from that?
So we don't explicitly do any correspondence, but we just we just do estimation for each of the pixel. For example, if you look at this ear, this line ear, we can know it. This is correspondence, right? The first frame and the second frame, there is a corresponding pixel, and both of them are estimated and mapped to a trajectory. And ideally, they should overlap with each other. But we don't force that. We don't first extract correspondence and force this alignment or overlapping. But we do separate. We do separate prediction in one forward pass on both of them. Yeah,
and that also explains what happens if like that. So I like the example of the lion's ear, because it's almost certainly going to disappear partway through a video like this, and then so that answers that question, because you don't actually need correspondence at every frame.
We don't need correspondence. And if there's a pixel that shows up and then it disappears and then goes back, you still get track of it.
Makes sense.
Yeah. Okay, this is about representation. And then the second problem is how we can acquire such a representation. Our solution is to also do this in an end-to-end way, just directly using neural network to map your input images or videos to this representation. And last year, I think the biggest thing in this field is this transition from Duster to currently faster VGGT and more recent Pi 3 and depth anything 3. And I think what this transition tells us is that instead of the pairwise inference, so if you think about Duster and even the traditional SFM, they use a pairwise paradigm. Each time you consider the relationship between a pair of images, and then you run a global alignment among all the images. But what faster and VGGT tell us is that you can run a one pass inference of all the input images, and using global attention, you can extract good information among all the frames, and they can interact with each other to model their spatial relationship. And this actually gives you better accuracy and also better efficiency, because you only need one forward pass of your neural network. So we decided to follow this that's insight and build things also upon this kind of global attention, global transformer. So the beginning of our pipeline is VGGT or faster style fusion transformer. So basically, you encode each image into tokens, and then you run fusion transformer to fuse all the image tokens with each other. And then you have your estimation head. And we actually initialize our image encoder and fusion transformer with VGT or faster, which means we can utilize their priors, their 3D priors, because they are trained on a lot of 3D data. So, and this prior is useful for 4D, for dynamic things. So we initialize our model with their weights. And then there is a difference. If you think about VGT, when they do this, when they use DPT head to finally make the estimation, they estimate point map from images, which means HW H by W by 3 to HW3. But what we did is kind of different. So trace anything model maps one image to D control point map. Let's see, we specify D control points for each of the trajectory, for each of the curve. Then you need, for each pixel, you need D control point to determine this curve. So that's why we do this, we do D mappings. We map images to D control point map, which means we map H by W by 3 to D by H by W by 3. So this is a major difference. So as you can see on the left, an input frame is mapped to D control point maps like this. And then you can do a curve evaluation. It's very basic mathematics. You have your control points, and each control point and each pixel have D control point. You trace out a 3D trajectory. So at atomic level, a pixel is first mapped by neural network to D control points, and then you do mathematics to evaluate this 3D trajectory. So you get the trajectory. And then you can also see this static things, this static objects, since they are ideally they should be mapped to degenerate trajectories. The estimation of their control points, they overlap with each other. So when you evaluate trajectories upon them, you only get they appear to be something static. Yeah. And then when you aggregate everything, you get the whole 4D representation of the scene. So basically, you have per pixel trajectories, and for each frame, and you get this only in a single forward pass, which would takes you like 3 seconds for 30 to 60 frame video, which can be quite fast if you consider those 3D tracking approaches. Okay, so this is about model design, and model design basically largely follows faster and VGT. The only difference is when you do this estimation from your DPT head, your estimation head, you actually do multiple mapping instead of a single one. And then I want to go back to the question why we use parametric curve like Bezier and B-spline. So here, the parameter of a Bezier curve is control point. And this has very good physical meaning. It is also a 3D point. So previously for VGT, you estimate point map, 3D point map. And now you only need to estimate control point map, which somehow align with each other, because the physical meaning, they align with each other. It is still 3D coordinate, only with different meaning. So that's why we don't choose other you have a lot of base function to model a curve. We don't choose linear base or like DCT based function, because their parameters, they don't have such a good physical meaning that aligns with our previous 3D geometric models. Yeah. So this is about this is about network architecture. Yeah. Then the final thing to get this to get this done is data. You need to build a data set to train this, because 4D data is quite scarce. We don't have a lot of reliable data at the time of development. So I built a 4D data platform to synthesize this data. So basically, it is a modular thing built in Blender. to drop digital humans into virtual environment, and users can have control over all these environments, characters, and camera trajectory, also the motion of characters. And it can support multiple tasks, not just trajectory field estimation, give you depth estimation, and also optical flow, 2D, 3D tracking. So this is a major source of the data used to train our model. And of course, we also use other open source, other public data set like Kubrick to train this thing. So that's everything. You have a new representation and a new network, and also a new data platform. And then all you need is you run your GPUs to train this model. And let's see. Yeah.
Sorry.
Go ahead.
But so the new data platform is all Blender, so it's like video game assets, and so you could train this all purely in simulation, sim to real, to get good and get.
Yeah. So I would say our training data is maybe not 100% synthetic, but yeah, so largely synthetic data, and
Cool.
and also only digital human. So you only see mostly like this human noise shape asset.
Right, because you led with the elephant, and so that still just the real world elephant that just falls out.
I would say that is generalization. Yeah, that is kind of amazing. Another amazing point, because this is only trained on this kind of human things, and it generalized to animals, to robotics, and other common objects. And that's why I also think this can be promising, because if you really scale up this data platform, I think this model have other potential and can do more interesting things. Yeah, but I would say we already seeing very good generalization among different domain. Okay, so maybe I can show some results. So here are some qualitative results. Take video as input. So basically, you can see we reconstruct the static part and also the trajectory each pixel traced out. Okay. And here you can see some hard like occlusion appears in this breakdance case, and also you have multiple dynamic objects here in this monkey scene, and yeah, it generalized to this furry animals. And our method, it can also take only an image pair as input. You don't really need a video. So image pair can also describe a movement, can describe a motion, and so our method is also applicable to image pairs, and image pair basically describes the motion, and the model need to interpolate between the starting state and the final state described by the two images. And you can see
I think this part is really interesting. Maybe potential for robotics. It's almost like, okay, this is your starting position of your robot. Maybe this is your goal image of the final position. Think of what is a reasonable trajectory, and then in a way that your trajectory feels here, it could be a potential one.
Yeah. To showcase this, we also have some robot things, because we really think robotics people may care about it. So you give them initial state of your robots, and you imagine or you specify a final state you want the robotics to be. You somehow need to estimate how to achieve this transition between states, and this trajectory is actually robots' ideal action to manipulate something. Yeah. Okay. Another input setting is this unstructured image set. So here, if you look on the above, you can see this image are unstructured. So they don't have continuous camera motion, and each of them are captured at different time step. If you look at this ball, at the first frame, it is in the air, and the last frame it is on the ground. But the model still recover the motion of this. And one thing, I show them in a time order for clarity. But when we input this to the model, there is no order, so they have to order it and give the recovery of the motion. Okay, yeah. So in summary, we have this trajectory field, a new representation, and the trace anything, which is a network to estimate trajectory fields. Our ambition is to push this into a 4D foundation model, which means it can not only solve your basic task of modeling dynamic things, geometry, and its motion. We want to apply this to other downstreams for robotics people and also for spatial intelligence. And yeah, so that's why that's why you're also saying robotics people might care about this. And I think some robotics guy term this as goal conditioned manipulation. So you give the model a starting state and also a target state, and you want a 3D trajectory or 2D trajectory. So here I'm showing 2D trajectories, which is projected from our 3D trajectory field. You also know it's 3D trajectory, and we haven't tested the accuracy of this in metrics, but that's our plan to do that. And considering you haven't the model haven't seen any robotics data, this result is I would say pretty good. And later we might want to scale up and also use robotics data into it, and maybe measure it in metrics to see whether we can really manipulate something. Use this. Another interesting thing we do is called motion forecasting. But to clarify, the forecasting capability is not from our model itself, but it's from a video generation model or image generation model. So the user, so you have maybe you capture a video of your robot, and user may have something in mind that want the robot to do, like move forward to the desk or move forward to the sofa. And then we leverage video generation model to generate this process to do forecasting in 2D. You forecast what happened in 2D as a video, and our model can elevate this into 3D. You actually forecast the motion the robot traces out like this. And here I have some more complicated motion, like first move forward and then return to the original position, or move back diagonally like this. Yeah, but this forecasting is not inherently our model's capability. But later we can consider also do forecasting in an end-to-end manner. Let's say you when you do reconstruction, you not only reconstruct the 4D trajectory of your observed time span, but you also do some estimation of a future time step. That can be challenging but also interesting. Another capability our model achieve is this spatial temporal fusion. Let's say in this input video, the camera is moving and the object, the human here, is also moving. And at some time step there is occlusion. Some part of the human body is occluded, but we still have its observation from other time step. Let's see, the left part of the body, we basically only acquire its observation from maybe the second half of the video. But what we can do is to build a trajectory field and then warp everything to a canonical frame, to the first frame of this motion. So this is another interesting application. Yeah, I think that's the end of this slides. We can do some more discussion upon it.
Yeah, I'm wondering,
I think this has so many applications for robotics, personally, Michael. Yeah.
I guess besides the like, you know, suggestion of like trajectory, you know, like you mentioned goal condition manipulation. I was also thinking like just like, you know, there are all these like egocentric video, like people, and then, you know, obviously inferring where your hands is in the video will be very important. I wonder how precise can this be?
Yeah.
Is it just a matter of just having a lot of very precise game data about hands and all that to get that?
First, about accuracy, as I said, that we haven't measured the accuracy on robotics in metrics, and we don't try to evaluate on robotics synthetic. But when we do this data platform, we also give a benchmark and to benchmarking the accuracy of your prediction of trajectory field, and in our align with our estimation format, and also to answer how you acquire such accuracy. I think it is still a matter of scaling up your data, and you're really learning the pattern of the geometry and also your motion. And also one thing I find important is the quality of the backbone model. Let's say we have faster of VGT as our backbone, and this is highly related to the quality of your control points accuracy. And as our team develop some more recent models, we find that this can, even when you have a stronger backbone, let's say we have a stronger backbone than VGT, this can even be better. We can have much better accuracy, especially in robotics or humanoid cases.
Yeah, I think the interesting thing here is also like you're saying basically the control map will still kind of work, even though in some part of the video, maybe some part of the, let's say, you know, again, egocentric video, I'm looking from, you know, the human perspective, maybe, you know, some part of it, the fingers is occluded, you know, halfway through, and then, but somehow is able to still connect the trajectory, even though at some part of the video it's being occluded, right?
Yeah. That's a interesting feature, I think. So let's say you have object in your hand, and you capture a video where some of the frame shows up, some of the frame it don't, like it is occluded by your hand. But the model can still recover the. I don't know whether it can always succeed, but it can still recover the object behind your hand, which means it somehow predict what happens under the occlusion, and this should not be should not be distracted from this single occlusion.
Just now you say something about like this run actually pretty fast, something about like 3 seconds to run. Was it like 60 frames or something?
60 frame, yeah, 60 frame.
Yeah, probably can't run, and this is on some consumer GPU, I suppose.
No, this is not. This is A100. I'm sorry.
Okay, got
One
it.
day
Okay,
of
got
run on
it.
consumer GPU.
Yeah,
But
I see.
Yeah, we haven't tried consumer GPUs, but that is, if you consider the number of parameters, it is comparable to VGT, because the only difference is the estimation head. So it is still comparable. But I can give you a concept. If you compare this to those 3D tracking method, the
How many
way
parameters is that, by the way?
I think it's around MB model.
Okay, so you could run that on a consumer GPU, definitely on like a Jetson.
That sounds good, but maybe not 3 seconds, but it is still good. Another thing I want to give you a idea is that if you look at 3D tracking method, there are ways each time they query one single pixel or maybe several selected pixel. They do this query and do one inference, and this inference can take you maybe longer than 3 seconds, can be maybe 7 or 10 seconds. But this only give you part of a pixel, very, very small part of the pixel. You have to run multiple inference, multiple queries to get the whole trajectory field if you compare the amount of estimation we do. So in the end, this can takes up to over 1 or 2 minutes to do the whole estimation. So still, I think this, and also we don't need other external estimators like depth estimator. We don't have optical flow estimator, and also we don't run optimization to do global bundle adjustment, which means this can also save a lot of work. So in the end, the whole computation is one inference of network. So I would say we still have advantage in efficiency compared to previous.
And I suppose it doesn't really matter how many objects are moving in the video, right? It would just, since it tracks all pixels in the image, you could have a video of a football team, playing football. Everything is moving, and yet it's gonna just trace all of the.
So it don't have a constraint on the number of moving objects or static objects, but of course it can get much harder when you have a lot of objects because the motion can be complicated, the occlusion can be complicated. A large part, not a large part, but a part of our training data is called kubric, where you drop different objects from the air to the ground, and for each scene you would have around 10 to 20 objects. Some are static, some are dynamic, and they can interact with each other. So this somehow gives the model the ability to handle multi objects. And when we do human training, our own data platform, normally we only have up to maybe 5 humans, so not a huge amount of head count, but still there are multiple human scenarios.
What would you say is some like limitation right now with this, or like maybe like scope for future work?
So I think one major bottleneck is still the data. So we only have time and resource to develop a data platform with digital humans. So I would say this model can perform best when dealing with human things. But when you have other fine structures like a robot dog, this cannot. I would say the motion can still be recovered good, but the geometry might not be as good because you have very, very, very fine structures. This is the first bottleneck. And the second is you cannot handle a very long sequence in one forward pass, because when you have, let's say, 10-second video, let's say just 300 frames, most of the case you either get a out of memory error, or you cannot you lose the track of the object or your pixels. And so our solution on that is to use sliding windows on different clip along the whole video. But that is not a deal, because if you run sliding window, you somehow you undermine one of the merits of our approach, which is first end-to-end, and you get track of all the pixels along the whole time span, because now you really need to find some correspondence at least among 2 sliding windows to get the whole representation. So that is not ideal. And that's why we are also thinking about how can this better handle long videos and complicated motions. And also another bottleneck is on the parametric curve side. Some of the motion might not be ideally represented by this kind of curve. For example, you have one you have one object that is initially static, but then after 1.5 seconds it starts to move. The parametric curve can get confused when we're modeling this kind of motion.
I suppose the action, like you're making like a shaking one of those bartender thing, that probably parametric curve will also really throw, right? Basically, it's kind of repeated like back and forth. Okay.
And you need to also, because we have our default settings, you have 10 control points to describe a trajectory. So you can imagine if you have more control points, this can maybe be modeled better. But of course, then you need more data and more complex motion in your data set to train this kind of model.
Yeah, it strikes me that it is a trade-off between what kind of hardware you want to spend on. Like especially for real-time robotics, you can put a LiDAR, then you don't use the compute, or you want to save on the LiDAR, and then you need a decent GPU. Hopefully, obviously the GPU will keep getting better, right? Eventually there will be an edge GPU, consumer grade, maybe even a Jetson, I don't know, like Nano 10 or something like that you can run these things quite fast. But LiDAR is also getting cheap. LiDAR gives you the depth.
Yeah, that is something. That is something I'm thinking of. So computer vision people, they always say this: you recover the 3D structure from images. This is an important problem. When I talk to friends who are working on robotics, they say if you want to perceive the world, you put a LiDAR on your robot. So you don't really
You get
you
a
don't
depth,
always need you don't always
yeah.
need to do this image-based reconstruction.
I
But what
think this is
LiDAR
changing, honestly, though, actually. Like, yeah.
I think
But I
one
mean,
thing
I do think there's a lot of egocentric video that will be collected going forward, like just pure video. So I think there's a lot of need for something like this as well to infer some kind of, I mean, use something like this, or maybe your colleagues are depth anything, right?
yeah.
Something like that would still be very helpful, I think, even though it's not done real time, but then, you're just trying to back out more information that is still three-dimensional and then use it to train.
Yeah. And I also assume what LiDAR gives you is the point cloud of the current time step, right? They don't keep track of the point's history. Yeah. So that's why this trace anything can help.
Yeah, but it's still very
There's
cool.
a
I mean,
longer
I
discussion
think,
about LiDAR versus cameras, but I think I really like the idea of using this for robotics in particular. Now it's probably not the time to get into that debate.
yeah.
I definitely come down more on the side of cameras these days, I think.
Yeah, camera. Well, yeah, I guess, I mean, obviously this podcast is mainly about robotics, but, like Chris and I do watch out for, any like significant advancement in computer vision, any foundational changes on the CV side, usually will have many downstream applications for robotics. So it's still very good to, like, the fact that you some of your samples are already using robotic arms, clearly you're thinking the same, is good.
Yeah, we actually had a paper on somewhat recently that was similar, like doing like flow fields for egocentric video learning, Amplify, if you remember that, Michael. Like, so I really do feel like this is could be such a powerful representation for robot learning, like for making ego video and learning skills. And I think it's really exciting stuff. Tons of potential.
Yeah.
Even from the super narrow robotics lens.
Yeah. Because there's going to be a lot of egocentric video, I kind of feel. Or maybe like wrist camera video, like both. Yeah, mostly just videos. Okay, cool. Well, I mean, maybe just to, I guess, wrap things up. Like, are there any like cool papers that you come across recently that kind of is pique your interest? You want to give a shout out to?
Yeah. So I would recommend Depth Anything from the same team. I think it is. It deals with mainly the static things, but it achieves. So like Depth Anything 1 and 2, they are basically molecular depth estimation approach. Depth Anything 3 is more like a VGT style model, but it gives you better accuracy, but also for multi-view reconstruction. But they also keep the good details of the molecular depth estimation model. So I think that is. And I also think the paper writing is quite good. So I recommend that paper. And also go back for dynamic things, one paper I like a lot is MegaSam, which use a different paradigm to do things, but still very powerful and more powerful than Trace Anything under some scenarios.
Yeah, sounds good. Well, thank you so much, Xinhang, for making the time. It's good to occasionally have
Thank you
vision
for
like
having me.
too.
Yeah, I'm having a lot of fun talking with you guys.
Okay, cool. Till the next one.
Sounds good. See
Thank you so
you.
much, Xinhang. Yep.
Bye-bye. Thank you.
Bye.